Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 5, Analytical Applications of Differentiation. Today's topic is 5.2, the Extreme Value Theorem. We're talking about global versus local extrema and critical points. Enjoy today's notes. All right, for section 5.2, we're talking about critical points. We're going to start by talking about a theorem that's called the Extreme Value Theorem. It says that if a function f is continuous over some interval from x equals a to x equals b, then f has at least one minimum value and at least one maximum value on the interval from a to b. What this is talking about, just sort of as some definitions that we're going to need, is we're talking about extrema. Extrema. If you've never heard of that word extrema, it is essentially a broad name for the maximums and minimums of a function. So the maximums and minimums of a function are the extrema. So extrema is like the extreme values, right? It's the most extreme. It is the biggest one, aka the maximum, or the smallest one, aka the minimum. And so what this extreme value theorem says is if we know it's continuous over that interval, then there has to be at least one minimum and at least one maximum on that interval. Now we could see this a couple of different ways, where we could have some function that sort of oscillates around, and we could see that, okay, there is clearly here in this picture a maximum value. It is the most extreme value, and there is some minimum value that is the most extreme minimum value. And so on an interval like that, we could visually see that that must be the case because it is continuous, right? There has to be some value that's the highest or the lowest. This is in fact also true for constant functions, right? If I have a function that is completely horizontal, like the lines say like y equals 5, in this case, what we consider, the extreme value theorem still counts, but we actually consider any arbitrary point on this line as a maximum or a minimum. They're all maximums and minimums on this point. They're all the highest one. They're all the lowest one, because the outputs of a constant function like this are all the same. It's guaranteeing that there is that maximum minimum, even when it's in this constant sort of weird case that we've got here. Now, in pre-calculus books and leading into AP calculus books, there's some different ways that these types of extrema are described. Sometimes there's the words global versus global or local extrema, or absolute and relative extrema. Global is the same thing as absolute. They mean the same thing. It is like the overall largest or smallest. So this is like overall largest or smallest. It is the absolute extrema for that. Local or relative extrema, those are synonymous. That means that it is largest or smallest, but just in an area. So largest or smallest in a, I'll put in quotes, local area. So it is just higher or lower than the values that are really close to it. Again, these are synonymous. Global and absolute mean essentially the same thing. Local and relative mean essentially the same thing. In AP Calculus and generally on, we will use these terms. I will not generally use global or local, but I'm just referencing them because some pre-calculus books do use those terms. So let's talk about this arbitrary graph that we've got over here. It's a piecewise function. We see some different parts. We see some discontinuities, maybe some asymptotes in it. But let's talk about what we see. If we're talking about absolute, right, we're talking about the overall largest or smallest points or y values on this, we can see that this point right here would be our absolute maximum. This is going to be our absolute maximum. And we know that because it is higher than any other point on this graph, right? It's absolutely the largest point on the graph. Similarly, we could see down here that this is our absolute minimum. On the graph, on the entire function, there is no point that is lower than that. That is the absolute minimum. Now, We can also take a look at some of these other ones and think about these relative ones. So we're going to focus now on the relative ones. We can see that this point right here is, from the points that are around it, it is lower than all of the points to the left of it. It's defined, even though it jumps up here, has that jump discontinuity. It is still lower than all of the points that are defined to the right of it. So on the left and the right, this point is lower than all of them. So I would call this a relative minimum. It is a relative minimum. Similarly, we might say, okay, hey, there's a vertex almost up here, but since this point isn't defined, we can't call that a maximum or minimum. It can't be a max or a min if it's not actually defined at that point. So this would not count. But actually, interestingly enough, this one would count as a minimum, because if I take a look at the points immediately to the left of it, they're all higher, they're all larger than this value, and all the points directly to the right of it are also higher than it. So this is actually lower than both the points to the left and the right. This is also a relative minimum. So both of those points on this graph would be a relative minimum. The only point that's sort of questionable on here, and in fact, I'll go for one more. This point down here appears to be sort of like a vertex that we got. It is defined. There's no open circle. That also would be a relative minimum here. All three of those would be cases of relative minimums where it is a point that is it is lower than all of the points to the left and right immediately surrounding that point. This point is a good question. There is a lot of debate within the AP Calculus community, and not just AP Calculus community, but Calculus community, on how it is defined and whether endpoints, whether you could have relative extrema at an endpoint. Could it be a maximum? Maybe. I'm going to say maybe, Max. It depends on your interpretation of it. Now, we can acknowledge, obviously, that this point right here is larger than all of the ones to the left of it. But there are no points to the right that are defined of it. So how would we say that it's larger from both sides of this function, that it's, therefore a relative maximum? But some textbooks, depending upon which textbook your class uses, defines it only on an interval. And so since the interval stops right here and it's only defined up to that point, and yes, this point is larger than all the ones to the left of it, they would define this as a maximum, a relative maximum for this function. Since there is considerable, difference in opinions based on like books and curriculums, the AP exam and College Board would never ask a question about one of the points on the endpoints, because they know, they certainly know like the debate on this, and they wouldn't want to give a problem that has multiple answers. That doesn't help them to do that. So they would probably just avoid problems like this, and they would not have, or at least they wouldn't ask about that point on the end. Great. Let's get into some practice. Find all extreme values, identify the type and where they occur. So what do we notice? First off, we notice that there is an absolute minimum right here of 1. So the minimum is 1, the y value is 1, and it occurs at x equals -3. So that is our absolute minimum. It is the lowest point on the graph. Also, we see that there's an absolute maximum. What's the highest point of the graph? It has a height of 5, and that occurs when x is equal to 0. That's this point that's up here. What other minimums or maximums do we have? We also have this point right here, which is interesting. We can define that as a relative minimum because it is lower than all of the points to the right of it and lower than all of the points to the left of that. So that would definitely be a relative minimum as well. So a relative minimum of 2 occurs at x equals 1. And that's about it. There's no more on this particular graph. No more maximums or minimums. No more extrema or extreme values. Let's try number 2. Number 2, we've got this function here. What do we see? We see that there's an absolute maximum of 3 at x is equal to -1. We see this point right here. that at x equals -1, it has an output of 3, and that is the largest value. Now this case, there's actually no absolute minimum. Because we see that it's sort of approaching this open circle, we know that it's going to get really, really close to it. It's almost like a limit. It's going to get as close to it as possible, but never actually get to x equals 1, comma -3. There is no point that is lower than the other ones. We can always get closer and closer and closer to that value, right? You could always add more and more decimal places, getting closer and closer and closer to -3. So there is actually no absolute minimum because this is an open circle here. But what about relative maximums and relative minimums? We see this point right here, which is clearly above the points of it to the right and above the points of it to the left, approaching x equals 1. So we know that there is a relative max of 1 at x equals 1. And then we've got our endpoint issue here. I'm going to just put here in parentheses, maybe we might say that there's a relative min of -1 at x equals 4. Again, that depends on your textbook and depends on your textbook and your curriculum and how your teacher teaches it. Great. Let's talk about this one right here. So what do we notice in this particular case? Let's think about what we notice about places where where there are maximums and minimums. I'm going to put a dot on every place where we see a maximum or a minimum. I see one here. There's a max. I see a minimum. I see a max. I see a minimum. And I see a maximum. The one thing that I would want to mention about this, like if we're thinking about what do we notice that these values have in common, is let's think about the slopes that are occurring at each of these. The instantaneous rate of change, aka derivative at this point, the tangent line has a slope of 0 for these first couple ones. And this one is actually undefined because I'll erase, but it was a cusp. And we know that at cusps you can't take the derivative of it. So that sort of leads us into this definition of what we refer to as a critical point, and then we'll come back to this graph to solidify our understanding of it. But a critical point, or a critical value, depending upon your curriculum, is a point, obviously, that has a possibility of being an extrema, aka max or min. And the way that we find a critical point or critical value is there are two cases. One of which is the first couple ones that we saw over here, is that where the derivative is equal to 0. So f prime of x is equal to 0. Those are what we refer to as critical points, places where the derivative is equal to 0. Or, like this last case that we have right here, where the derivative is undefined because it's like a cusp, or there might be something else going on. So f prime of x is undefined, or does not exist, depending upon how you want to write that one. If we know that the derivative is 0 or it's undefined, we refer to those points as critical points. And again, critical points are important because they're places where they might have extrema. They're places where we can look on a function where maximums or minimums might be occurring. And so it's nice to be able to identify those using the derivative of a function to have an idea of where those values come in. One sort of note that I want to mention that comes up occasionally is that critical points must be in the domain of the function. Sometimes when we're working with equations, we get like possible critical points, and it's always important to make sure that you're checking to make sure that these values are these critical points are actually in the domain of the original function that you were starting out with. Yep, that's worth checking. We'll see that in one of the examples coming up, I think here, number 4. Great, let's try this for number 3. So number 3 says f of x is equal to 1/3 x cubed minus 9x plus 24. Find all critical points. So again, we're looking for places where f prime of x is equal to 0 or it's undefined. So let's start off with the derivative of this function. F prime of x, if we do the power rule for this, is going to be, what's that? Just x squared minus 9. And we want to find out, first off, we can see that there's no values that would make this undefined, right? There's no like denominator that could be 0 or anything like that. So really I want to see where this is equal to 0. So x squared minus 9 is equal to 0. I'm going to factor that. We've got a difference of 2 squareds here. So that's going to occur at x equals -3 or +3. And both of these, this appears to be a well-behaved function. There's no reason why I wouldn't be able to plug in either of these numbers into this. So these are our critical points. They are possible places that if I were to graph this function, that I might see a maximum or a minimum occurring. In fact, if we do graph this function, we would see, one of these being a maximum and one of these being a minimum at those values. But again, it's not a guarantee, right? It's only a possibility of there being an extrema at that point. There are places we want to look. They are critical points because we might be able to find extrema there. Great, let's try number 4. G of x is equal to 1 divided by the square root of 4 minus x squared. We know we're going to need to take a derivative because to find the critical points, we're looking at the derivative of this. So one way we could do that is to rewrite this denominator as, this is the same thing as 1 over 4 minus x squared to the 1/2 power. And because that's in the denominator, that's the same thing as 4 minus x squared to the -1/2 power. So rewriting it in this way allows me actually to use the chain rule to take the derivative of this function. And so throw back to chapter 3, let's do that chain rule. G prime of x by the chain rule is going to be -1/2 of times 4 minus x squared raised to the -1/2 minus 1, so that's -3 over 2, times the derivative of the inside of this parentheses. So the derivative of 4 minus x squared is -2x, and that's going to be our function for the derivative. If we simplify that, we have -1/2 times -2 over x. The negatives are going to cancel, the 2's are going to cancel, and so I'm left with just an x in that numerator. And then in the denominator, we have this expression, because it's a negative exponent, it's going to move down to the denominator. That's going to be the square root of 4 minus x squared cubed. So by moving that to the denominator, it made it positive, and then because it's a 3 over 2, the over 2 is the square root, and then this is being raised to the 3rd power. So that is our g prime of x. Now, here's the question. How to find the critical values? We want to think of what's going to make it either equal to 0 or make it undefined. We can see that simply having the numerator be 0 would give us a critical point. So if x equals 0, then g prime of x is equal to 0. So that's a critical point. Also, we want to think about where this would be undefined, right? Since there is a denominator here, we can see that there might be some values here that might make us divide by 0, which of course we can't do. And so what is that going to be? That's going to be places where 4 minus x squared would equal 0. And so -x squared is equal to -4. So x squared is equal to +4. So x is equal to 2 or -2. This is, so these are again places where, so I'll say at x equals 2 or -2, g prime of x is undefined. So we have some candidates here. Let's take a look. So x equals 0 and x equals 2 or -2. this is where we're going to get into the note that we were talking about earlier over here, where we said critical points must be in the domain of the function, right? So these are obviously places where the derivative is equal to 0 or it's undefined, but are these x values part of the domain of the function? We can see here that if we plug 0 in for the function, that there will be an output. This looks like it would be 1/2 if we did that. So like 1 over the square root of 4. And so that's 1/2. So x equals 0 is definitely in the domain. However, if I plugged in 2 or -2 into this function, we can actually see that the 2 squared would give us 4. So 4 minus 4 would be 0. It would cause us to divide by 0 if I plug either of these in. So even though these two x values make this derivative undefined, these would not be considered. These would not be considered critical values because they are not part of the domain. They are not part of the domain of g of x. So they don't count. So our only answer for this one, in fact, is x equals 0. That is the only critical value or critical point for this function. That's going to be it for today's notes. Try our practice, check the solutions for that, and good luck on your mastery check. Have a great rest of your day, and take care.